Using larger orifice sprinklers also increases the density. The orifice restricts the amount of water flowing from the sprinkler. When water flows between 2 points, friction loss occurs. How much pressure is lost depends on the diameter, the length, age, and interior condition of the pipe.
Here we have 3 tubes. The one on your left is 1/2 inch in diameter. The middle one is 3/4 of an inch. And the one on your right is 1 inch in diameter. We'll open the valve and allow water to flow through the tubes into the containers. We can see that the 1 inch diameter tube permitted more water to flow, giving us higher density.
We have just taken a basic look at sprinkler density and some ways to increase it. However, evaluating density requirements, calculating the system's ability to deliver the increased density, and determining the best method of achieving it is anything but simple.
The deflector forms the discharge pattern based on its orientation to the piping. A head that points upward, or an upright head, should have a deflector that directs the water downward. It is critical to have the correct head installed based on its orientation. Firefighters should be able to recognize when an improper head is installed so that corrective action can be taken to ensure effectiveness of the system. In addition to forming the pattern, the temperature rating of the head may be stamped on the deflector.
We're going to take a look at these sprinkler protection options. We'll contrast and compare the ESFR, the large drop sprinkler, and the standard sprinklers, which include the 1/2 inch, 17/32 inch, and the ELO or extra large orifice sprinkler. There are many variables that go into developing a good protection scheme. Factors such as the type of commodity being protected, building construction, storage arrangement, storage height, ceiling clearance, aisle width, and many more contribute to the complex picture that helps shape each protection option. Until the ESFR, or Early Suppression Fast Response Sprinkler, was developed, all sprinklers operated under the principle of fire control. The idea is to limit the fire spread by pre-wetting the surrounding merchandise until a hose team could arrive and put it out. Sometimes 30 to 40 control mode sprinklers would operate during a fire, creating a lot of water damage. The ESFR, on the other hand, operates very successfully under the principle of fire suppression. It's designed to quickly respond to fires in the earliest stage of development and deliver a heavy sprinkler discharge onto the fire source itself, in effect, suppressing it. Research has shown that this approach results in a much smaller fire with fewer sprinklers operating. As a result, the need for pre-wetting the surrounding storage is reduced, lowering the amount of water damage. In terms of protection level, the ESFR is suppression mode technology, which generally results in less smoke and water damage than control mode technology, and it's designed to operate without in-rack sprinklers. Large drop sprinklers came about as a result of a study begun in 1968 by Factory Mutual on the performance of sprinkler sprays and water drop size. As the name implies, the sprinkler is designed to produce a heavy discharge of water droplets. Research showed that large drops, along with sufficient water pressure and adequate sprinkler distribution, were able to penetrate the strong updraft generated by a severe fire. During the testing of the large drop sprinkler, it was hoped it would be the first generation suppression mode sprinkler. Unfortunately, research showed it just wasn't quite up to the task. Large drop is control mode technology. So if you have them at the ceiling only, you can expect moderate smoke and water damage depending on the type and extent of the fire. When used in conjunction with in-rack sprinklers, you can expect less. The standard sprinkler has been around now for over 100 years. It was originally designed to protect against hazards in manufacturing environments, such as those found in textile mills, and it was soon applied to warehouse environments as well. But after the 1950s, changes in warehouse storage practices, ever-increasing storage heights, along with the increasing use of plastics in all types of products, soon exposed their performance limitations. Despite this, standard sprinklers continue to provide useful, low-cost protection for certain storage arrangements. There are 3 types of standard sprinkler. All of them are defined by their orifice size. half-inch, which is the oldest, 17/32 inch, which was introduced in the early 60s, and the ELO, or extra-large orifice sprinkler, which was introduced in the 1980s. Basically, the ELO sprinkler is an improvement on the 17/32, which was in its day an improvement over the half-inch. In terms of standard sprinkler evolution, the ELO represents the latest technological refinement. It's designed to take advantage of situations where there's a low-pressure, high-volume water supply. It also eliminates the need for a booster pump in those situations. All standard sprinklers are control mode technology, so depending on the type of fire, you can expect moderate to high smoke and water damage. When used in conjunction with in-rack sprinklers, you can expect less smoke and water damage. So there you have it, all the possibilities for protecting anything up to and including plastic.
The NFPA standard dictates what type of piping will be used. The piping that you are most likely to see is steel and plastic, with plastic being found primarily in residential installations. Regardless of the material that makes up the piping in the system, the components all have specific functional names. There are many different types of valves in a sprinkler system. They can be broken down by function as control valves and operating valves. Valves can also be described as indicating or non-indicating types of valves. Indicating valves are designed so that inspectors can determine valve position, open or closed, simply by looking at the indicator built into the valve. Control valves turn off the water to the system for maintenance and repair. They may also shut down the entire system or may be zoned to control small sections. Either way, these valves are usually indicating valves so that the inspectors can determine valve position, ensuring that the system is in service. Furthermore, there is normally some type of tamper device attached to prevent closing the valves maliciously without detection. This security may be in the form of chains and padlocks holding the valve wheels open, or may be electronic monitoring devices that measure water flow or valve handle position. Operating valves help control the flow of water through a system in a systematic, forward manner. These valves may also be of the design to automatically drain portions of the system to prevent freezing or other damage.